It's time for chapter 3, and in chapter 3 we're going to look at all the things we can do with derivatives. And for the most part, these sections will all revolve around maximum and minimum values. And if you think about it, this is one of the main reasons why we care about derivatives, because if you have some sort of function, say that function's calculating revenue for your business, or that function's calculating the strength of your materials if you're an engineer, or any sort of type of problem you might solve. The most important points on the entire function are the maximum and the minimum points, because you want to know what's the biggest the function can ever get and what's the smallest the function can ever get. And so problem after problem after problem, these are the most important things. And it turns out that derivatives are central to figuring out where maximum and minimum values are. So to do this, we're going to start with two terms. The term absolute maximum and minimum. And so we have an absolute maximum and then a local maximum. And these are going to be the two kind of terms that we start the day with. And to do this, let's start with a graph. If you hear that dinging, my son is doing his math problems, and whenever he finishes a problem, he rings the bell. So that's very exciting. So I don't know if you heard that or not. Okay, so this is a function, and I think that if I just gave you the picture of the function and said, hey, can you find the maximums and minimums? I think you could. And the first thing we would recognize is that this is the maximum. This is like the largest that the value ever gets. Meanwhile, the minimum, well, there's kind of a little bit of a debate what to do. Maybe the minimums occur here, where it's like negative infinity because it goes forever. But there's also something that's kind of acting like a minimum right here. It's smaller than the things around it, but it's not smaller than these two tails. Similarly, there's this point right here that acts like a maximum. It is larger than the points around it, but it's not as large as this maximum. And it turns out that that distinction is the difference between local and absolute maximum. So this is the absolute. Maybe I'll write in black. I find that hard to read. This is the absolute max. And this is the local max. This one is a local minimum. And for the absolute minimum, I guess you could say negative infinity, but we would probably just say there's no absolute minimum. So you can have problems where you have absolute maximums and you don't have absolute. So you can have absolute maximums and mins, but you don't have to. And so local, so what's the difference? The difference is the absolute max and min is the largest value on the entire domain. So for the problem I just showed you, is the largest value from negative infinity to infinity. For the problems we'll do today, though, we'll take smaller domains, and we will take points where it's just, we'll just take, say, the numbers between 0 and 1 or something like that. So we'll make it smaller. And a local max is just larger than all nearby points. This word nearby is kind of a subtle term, and this is a term it takes a lot of time to piece out. And this is this discussion of what does nearby mean is a discussion for an advanced math class, particularly the math class called real analysis. Okay, so absolute max, largest value in the entire domain. Local max is just larger than all of your nearby points. Okay, so let's come over here and let's look at this one more time, and we're going to make an important observation. And that is, if I look at these 3 points, these two they're not really points. They're kind of continuations on forever. But if I look at these 3 points, what do we notice about the derivative at these points? I want you to ask yourself that question really quick. What is the derivative at a maximum or minimum value? What is the derivative at a maximum or minimum value? Well, what's important, so let's look. So hopefully you've asked yourself that question. Notice, what is this derivative? Well, what am I going to do? I'm just going to draw a tangent line here, and I'll notice that the derivative is 0. What if I look at this point here? What do I get? I get 0. And this point, well, this one isn't 0. This one is one where f prime of x does not exist. So what you'll notice is that every single point, if you have a max or a min value, one of two things happen. Either f prime of x equals 0, or f prime of x does not exist. And you can kind of guess right now that based on the types of functions we've seen this semester, the types of functions we're most used to, this example where they're equal 0, that's going to be the example that shows up most often. But does not exist, can happen, and it's important to know that this is a possibility that your derivative could not exist. But equal to 0 tends to be the one that gets the most, that happens the most often. So because of this, we call these points critical numbers. So a critical number is any point of any value of x where one of two things happen: f prime of x equals 0, or f prime of x does not exist. So we call these critical numbers because these are important. Now I want to make a really important observation, and that is that we know one thing is true, that maximums occur at critical numbers. Always occur at critical numbers. So let's think about that. So if I have a picture that looks like this, then that maximum has to be either 0 or not equal to 0. But I want to make a quick observation. I'm going to write this. I'm going to write this in. I was going to do red, but let's do green. Maximums always occur. However, some critical numbers are not maxes or mins. So every max and min is at a critical number, but not every critical number is a max and min. So if we try to turn that sentence around, that's not always true. So let's think of an example. An example is something that kind of looks like a cubic function. So notice this point right here, this is a critical number. But it's obviously not a max or a min, because it's obviously a critical number because the derivative is 0 at that spot, but it's not a max or a min because it gets bigger to the right and smaller to the left. So one way of thinking about this is you've got all of your critical numbers right here, and then your maxes and mins are inside of your critical numbers. But there are some critical numbers that are not maxes and mins. I don't know if that picture helps. So I'm going to erase it before I confuse anyone too much. If it helped, good for you. Okay. So let's take just a moment and find some critical numbers for a problem. And we're going to do that problem 3.1. So what you should do right now is you should probably pause your computer and at least try to take the derivative of 3.1. And then after you take the derivative, you should try to find your critical number. So now's a good time to pause and come right back. All right, so this one is f of x equals 8 times the cubed root of x minus the cubed root of x to the fourth. First thing I want to point out is I would not write this function like this to try to find the derivative. I would write it as 8x to the 1/3 minus x to the 4/3. And I do this just because these powers are so much easier to work with than the other way around. Okay, now once I have this, I'm ready to start attacking my problem. And how will I attack my problem? I will attack it by taking the derivative. So I'll do f prime of x. And f prime of x is 8 times 1/3 times x to the negative 2/3. So 8 x to the 1/3, x to the negative 2/3 minus 4/3 x to the 1/3. At this point, you've all passed your derivative tests. You all are all really good at this. So this makes sense. But now the algebra starts to get a little messy, because what do I have to do? I have to figure out when is this thing going to be equal to 0? And so, or when is this thing not going to exist? So let me rewrite this one more time. And I'm going to rewrite this as 8 divided by 3 times 1 over x to the 2/3, because that's what the negative sign means, minus 4 over 3 times x to the 1/3. Now first, I want to notice, where does f prime of x not exist? Does not exist. If you look closely at this problem, you'll see only one potential thing. So it does not exist. All we have to really do is look for potential problems. Problems occur when we take square roots of negative numbers, where we divide by 0. And really, almost every single time we have an issue in these problems is where we're dividing by 0. We can also have things like where you have an absolute value, where you have a piecewise function and those pieces don't meet up. But for us, the majority of the time is we're dividing by 0. And I see one place where we're dividing, and I say it does not equal 0. It does not exist if x equals 0. So x equals 0 is one of those critical points that's a problem. Okay, so it does not exist at x equals 0, so let's keep going. Now, the next thing we need to do is figure out, where does this equal 0? So I'm going to do 8/3 times 1 over x to the 2/3 minus 4/3 x to 1/3 equals 0. And I'm going to go, okay, well, how do I get a hold of a problem like this? I know this algebra is tough, and I know that a number of you are probably not pumped or excited about it, but there's a really easy thing we can do right now, and that is we can multiply everything by this x to the 2/3. So if I multiply by x to the 2/3 on both sides, let's multiply everything by x to the 2/3. The good news is this right-hand side stays 0. The left-hand side looks like this. Looks like 8/3 times, well, that ends up canceling, and we end up getting 1. That's why we did it. Minus 4/3 times x. What is x to the 2/3 times x to the 1/3? Well, those powers add, because you know when you multiply powers, they add together. And so this is x to the 3/3, but that's just x to the 1, which is just x all by itself. So this is just x. So we've got 8/3 minus 4/3 x equals 0. And this is not a really bad algebra problem. So now we're in really good shape. So negative 4/3 x equals negative 8/3. Divide by your 4/3, and x equals positive 2. So x equals positive 2. So what are our critical numbers? So what are our critical numbers? Our critical numbers are x equals 0 and x equals 2. So we got two critical numbers for this problem. And this is an important skill, so it's really important that you can take equations, even ones that are a little messy, and go do this analysis and find out where the critical numbers are. Okay. So let's take just a minute and look back and think about the types of problems that we're going to be doing today. So the types of problems that we're going to be focusing on today are problems where we have a domain, a closed region. So we have a closed interval. A closed interval, and that's where we put these brackets and we put numbers on here with an a, b. And I want to notice something about a closed interval, and that is when I had this problem from earlier, I had no absolute minimum because I was going on forever. But what if we closed that interval and I said, like, this is A and this is B? Then what would that do to our picture? Our picture would now have a closed dot here and a closed dot here. And what do we notice? We notice that now our maxes and mins could occur at any of these critical points, or they could occur at these endpoints. So when we have a closed interval, we make a real quick observation. And the observation is this: every max or min must be at either a critical number or an endpoint. And hopefully that makes a little bit of sense. I'll draw one more picture just to illustrate this, right? If we've got our graph, and our graph looks something like that. Okay, let's stop right here. If our graph looks something like that, then what you notice is we have critical numbers here, we have a critical number here, we have a critical number here. Well, where do our max and mins occur? Our min is right here, and our max was right here, but our potential spots are just those 5. Now, why is this good? This is good because when we started the problem, if you just have a graph, and I take every number between A and B, there are an infinite number of choices. And so your critical number could be any of an infinite number of things. But now, by just doing a little bit of analysis, I know the max and min have to be at a critical number or an endpoint. So now I have just 5 choices. And if you have just 5 things, it's easy to figure out what the biggest of those 5 things are. Okay, so this kind of gives us our method for finding a maximum or minimum. So our method is what's called the closed interval method. And our closed interval method looks like this. We find the critical values, we locate the endpoints, and then we plug all of these. So everything that's a critical value or an endpoint, we plug it into f of x. Now, what's important is this is not f prime of x, because if we plugged in f prime of x, if we plugged the critical values in f prime of x, we would either get 0 or does not exist. So we wouldn't learn anything. We're trying to find the largest value of f. We're trying to find where that function hits the biggest value. So we plug these numbers into f of x, not f prime. Why am I making a big deal about this? In a couple sections, we're going to do some problems where we plug into f prime of x. In those sections, we're not trying to find maxes. We're trying to find where the function is increasing and decreasing. And so we'll be changing the problem just a little bit in just a few sections. So try to keep these things straight. Try to kind of keep all these ideas clear in your mind as we go through. Okay, so this is the closed interval method. Let's take that problem we did just a second ago and do the closed interval method on it. So I'm going to make up a problem. I'm going to make up a problem that for us. So this is not in your notes, but it kind of complements 3.1. So we'll do 3.1. How about 3.1 star, we'll call it. Okay, 3.1 star. We'll let f of x be this, and we'll say find the absolute max and min of f of x on the interval. And the interval we're going to choose, let's go from -1 to +2. How does that sound? Sounds like a pretty good. Let's not do +2. Let's do 8. You know why I chose 8? Because I know what the cubed root of 8 is. I don't know what the cubed root of I don't know what the cubed root of 2 is. Okay, so find the absolute max and min of f of x on -1 to 8. Okay, so that's our region. And so how do I solve this problem? Well, the first thing that I do is I find all critical numbers. Step one, find all critical numbers. Well, the good news is I already did that. So here's what we did earlier in the problem. So earlier we found 0 and 2. So this step is where you would go through all of the algebra that you would have done earlier. So the answer here is x equals 0 and x equals 2. That's what we got for those critical numbers. Okay. The second part that we would do is we would find the endpoints. There's no finding here. The endpoints are given to you. The endpoints are this -1 and 8 that are right there. So what are our endpoints? Our endpoints are x equals -1 and x equals 8. I'll put commas here so it doesn't look like I'm adding them or something. Okay, so find critical numbers, 0 and 2, find endpoints, -1 and 8. And now then, the last thing that we do is we plug into f of x. So what does that mean? It means I need to take all 1, 2, 3, 4 of those points and plug them into f of x and see what I get for my values. So let's start plugging in. So we'll plug in f of 0, we'll plug in f of 2, we'll plug in f of -1, and we'll plug in f of 8. So we'll plug all those in our original equation and see what we get. So this is 8 times the cubed root of 0 minus the cubed root of 0 to the 4th power. This is really easy to figure out. 0 is what we got for our answer. Okay, 8 times the cubed root of 2 minus the cubed root of 2 to the 4th power. Oh, well, I still have to do 2. Oh, okay, so I still have to do 2, so I have to plug that in. Give me just a second on my calculator. Okay, so I'll do 8 times that answer minus answer to the 4th. I got 7.55 is what I got for this. Hopefully that's right. I got 7.55 for that answer. And now I've got -1, so that's 8 times the cubed root of -1 minus the cube root of -1 to the 4th. Notice this ends up being -8 because this is just a -1. This is a +1, so this is -8 minus 1. So I think we get +7 here for that number. I hope. I think that's right. And then finally, we'll do f of 8. And so that's going to give me 8 times the cubed root of 8 minus the cubed root of 8 to the 4th. This looks really bad, but the cubed root of 8 is 2. So this is 8 times 2 minus 2 to the 4th. And, oh, this ends up being 0 as well. So I think if I... maybe if we graph this, we could see it, but too, I'm just going to go with this as my answer. So what we see is we have our answers, and all I have to do is I have to look through and I have to say what's the biggest and what's the smallest. Notice that these zeros are the smallest, so 0 is the absolute min at x equals 0 and x equals 8. So that minimum occurred twice on our function. So twice we had that minimum occur. And then which one's the largest? This is the largest. So 7.55 is the absolute max at x equals 2. So the max was at 2 and the min was at 0 and 0. And tell you what, let's plug this in our calculator so we can look at it and compare. So what am I going to do? All I'm going to do on my calculator is come here, and maybe you can see this. I'll just clear this. I'll just type that equation in. So I'll do 8x. I'm not going to try to find the cubed root button on my calculator. Let's just do that. 8x to the 1/3 minus x. Oh, that's not an x. Minus x to the 4/3. There we go. I'll just go with that. So 8x to the 1/3 minus x to the 4/3. Let's grab my window, and I only want to go from -1 to 8, and so I'll just make my window -1 to 8 so I can see the whole picture. And then the last thing I'm going to do is I really like this button called Zoom Fit. It's right down here. What Zoom Fit does is it takes your window and automatically scales the equation to look to be the right size on that window. So here's our -1. We come up. There's that. And then oh man, I messed up somewhere. Oh, I see how I messed up. You all see how I messed up? Notice I'm looking at my graph. I see I got the wrong answer earlier. What did I get the wrong answer? Well, the wrong answer was because of this. Look, this is -8 minus 1. So this is actually -9 right here. So I get -9 on that spot. And so my minimum was neither of these spots. My minimum was right here. Wow, I would have got the wrong answer if I hadn't graphed it. I'm glad I graphed it. So those of you who caught me during the video, way to go. You all did great. Bonus points for you. So the absolute minimum at x equals -1. So this is the actual answer, and here's our graph. So when we look at our graph, you can kind of see what's going on this graph. You can see that the minimum occurs right here on the left-hand side. We have the place where the derivative doesn't exist because it's vertical right here. You have the maximum right up here where the derivative was 0, and then you have the other endpoint down there. And that was our maximum, and that was our minimum. So you can see our two values. Well, I hope that was kind of interesting. What we're going to do now is I'm going to go through problem 3.2, 3.3, and 3.4, but I'll do these on separate videos so that you can click on just the problem that you're interested in. They will get successfully harder and successfully more interesting. So try all 3 of those problems and then watch my video so that you can be on top of it. But what do you need to do? For each video, for each problem, you need to go through this step. You need to find the critical values, locate the endpoints, plug them in, and then all we're doing is we're looking for the biggest and looking for the smallest. So see if you can do that. Good luck, and I'll see you on problem 3.2.